finishing up this problem where we were finding points of inflection. Points of inflection are where f double prime of x equals 0 or undefined, and your signs of f double prime have to change. So it either has to be negative to positive or positive to negative. It doesn't matter which. What I've done so far is I have rewritten f double prime of x as its fraction. This is how I would recommend plugging it into a calculator, like f double prime of x equals, or like the y equals would be this, 10 over 9 x to the 1/3 power. You might have to put that in parentheses if you have an older calculator that does like the caret and then the exponent. Like if that's what shows up on your calculator, you'll need parentheses to get that whole fraction in the exponent. Plus, and that's a negative 1/3 power, plus 10 over 9 x to the parentheses exponent, right? Negative 4/3 power. That's how I'd recommend, so you don't have to do the square root, or the, cube root, but you could do a cube root if you really felt like it. You have to go into math to get the, hit the math key to get the cube root instead of a square root. All right, the next thing you're gonna do is plug in 2. So you can do that several ways. You can go into second calc, and then number 1 is value, and you can type in a -2 and hit enter. Or from the home screen, you can do that like y1, like the y vars thing, y1 of -2. So you've got to do parentheses to type in -2 as your x value there. And y1 represents our second derivative. Okay, so second derivative at -2. I'm not going to show you all the calculator stuff, but you end up with a negative number. You end up with a positive number for -0.5, and you get a negative number for 1. Our goal was to determine points of inflection. We have points of inflection at x equals -1 and 0 because f double prime of -1 equals 0, f double prime of 0 is undefined, and f double prime of x changes signs. Right? At -1, your second derivative changes signs. At x equals 0, your second derivative changes signs. So if it was plus plus or minus minus surrounding this spot, you would not have a point of inflection. It was a possible point of inflection, but it didn't work out. Then it says discuss the concavity. I'm going to say on and then leave a blank. F is concave up because f double prime is positive. And on blank, f is concave down because f double prime is negative. Negative down, positive up. If you have a positive mood, you're concave up like a smile. If you have to draw it out, hey, there's a smile, you're in a positive mood. Fantastic. So where is f double prime positive? Just between -1 and 0. -1, 0. And concave down from -infinity to -1. And again from 0 to infinity. Because f double prime was negative. I like writing out the sentences first and then plugging that stuff in so I remind myself what I'm looking for in my math. Okay, last bit here is the second derivative test. So the second derivative test, just like the first derivative test, tells us something about our graph of f of x. Okay, so let's say that f is a function so that the first derivative is 0 and the second derivative exists. So it's not like up here where we ended up with that undefined bit because a denominator equaled 0 in the second derivative. Okay, so first derivative equals 0. What does that mean? It means that you have a horizontal tangent line. And that means one of three things. You're either a maximum or a minimum, or like in the case of y equals x cubed, 0 has, x equals 0 would have a slope of 0. And same thing this direction. So it could be a critical number at whatever c is. So it could be a critical number, but not a max or a min. So these are the possibilities: max, min, or just a critical number. Okay, if we know that f double prime is positive, so your graph is concave up, in the interval surrounding our critical number. Okay, so in the interval surrounding our critical number, the second derivative is positive. Our graph is concave up. So which picture does that look like? In this one, surrounding our critical number, our graph is concave down. Here, surrounding our critical number, our graph is concave up. Okay, so is that point a min, a max, or neither? It's a minimum. So number 1 has a relative minimum at that x value and y value. Number 2, f double prime of c is less than 0, so concave down. That's going to be this first picture. Concave down, and the first derivative, meaning the slope of the tangent line, is 0. At that point, we have a maximum, relative max. Then number 3, if f double prime of c equals 0, so the second derivative is also 0, so not positive or negative, then it tells you nothing. The test is inconclusive. This is kind of a harder one to wrap your mind around. Inconclusive test. We don't know if we have a maximum, a minimum, or one of these situations going on. We just don't know. So you cannot use this test when f double prime of c equals 0, because you don't know if you have a smile or a frown, or if it's some other weird situation like that x cubed deal. It tells you nothing. So you cannot use this test. You have to use the first derivative test instead. It does not mean that there's no min or max. The test just does not work for that function. Okay, so it's not positive, not negative. We just don't know. We are going to use the second derivative to approximate f of 1.1 for this function. We're going to use the tangent line at x equals 1. This guy is a little bit weird, but we want to know if our function is an overestimate or an underestimate. So is that y value that we get an overestimate or an underestimate? Okay, so what is happening here? We've got this function that is y equals 3x squared plus 2. Our second derivative would be a positive number, right? Multiply 2 times 3 is 6, and then our second derivative would just be literally 6. So we have a smile, which if you think about quadratics, if a is positive, you have a smile. So it looks something like this. Plus 2, b 0, so 1, 2. Okay, you do not have to know what the picture looks like. It just so happens that this was kind of an easier one to draw out. We are going to find the tangent line at x equals 1, and we're going to use that to approximate f of 1.1. So tangent line at x equals 1. x equals 1 is like here. The tangent line looks something like this. Okay, so if your tangent line at x equals 1 looks like that, we can use x equals 1.1, and we can use the tangent line to get a point that is super, super close to x equals 1.1. Super, super close. So the y values are very close to each other because the x value is very close to the point of tangency. You might notice that the line is underneath your curve. So the y value that we get as the estimate from the tangent line is going to be less than the y value that we would have gotten from literally just plugging in 1.1 here. Now, there is a reason to doing this estimate, and it's that if we have a really, really complicated function and it's hard to plug in like 1.1 here for x, then the estimate will just get us really close to the correct y value. This point would be called an underestimate. We already know that that's what that's going to be, but I'm going to give you reasoning for that to justify. Okay, so let's start by finding the first derivative. So f of x equals 3x squared plus 2. F prime of x equals 6x, and f double prime of x equals 6. Oh, yeah. What are things that we know? We know we can find the equation for that tangent line. How do you find an equation of a tangent line? Well, it's like y minus equals something times x minus. Okay. We want to find the equation of the tangent line at x equals 1, because it says use a tangent line at x equals 1. That's what we're going to do. So 1 comma what? We need the y value for here. So we need the point of tangency. So that's going to be f of 1, which is 3 times 1 squared plus 2, which is 5. So y value is 5. That goes here. We also need the slope of the tangent line, which is f prime of 1. F prime is 6x, so this is 6 times 1 equals 6. Our slope is 6. There it is. You do not want to switch that equation of a tangent line into slope-intercept form. You want to leave it as point-slope form, and here's why. We are about to plug in 1.1 for x. So our first step was find the equation of the tangent line. Find equation of tangent line. That's step 1. At x equals 1. So you had to find the point of tangency, slope of tangent, line, and equation of tangent. Number 2, we are now going to plug in x equals 1.1 and solve for y. These steps are going to be useful in future problems. You'll just be plugging in different x values. Okay, so let's plug in 1.1 for x. So this equation is going to turn into y minus 5 equals 6 times 1.1 minus 1. 1.1 minus 1. So y minus 5 equals 6 times 1.1 minus 1 is just 0.1. Multiply here, y minus 5 equals 0.6. And then add 5 to both sides, y equals 5.6. This is an estimate. F of 1.1 is close to 5.6. So we did not need a calculator for any of that. We plugged in 1.1 for x, subtracted, multiplied, and then added to get y completely by itself. So this 1.1, 5.6 is, zoom back in slightly, that is this point, 1.1, 5.6. We know that that point is lower than the actual point, 1.1 comma something, that is on the curve. It is lower. So we have found the estimate. It was 5.6. So I'm going to box that in. So how do we know that we have an underestimate? Okay, we have an underestimate because our graph is this shape and the tangent line is below. So I'm going to draw something out for you, and this is going to work for all of your future pictures for any time you do one of these guys. So let's draw a graph where F is concave up and F is increasing. Let's start with decreasing, so then I can draw one picture. Decreasing. And then over here, we're going to do F is concave up and F is increasing. Concave up looks like this, right? Concave up. This half of it is decreasing. This half of it is increasing. Then I'm going to draw a frown down here. This half, F is concave down, and F is, let's see, it's moving up as we move to the right, so that is increasing. And here, F is concave down and decreasing. All right, let's draw a tangent line. So that's going to be slopes. Let's draw a tangent line at any point in the little quadrant. Okay, now look at the line. Is the point, any point on the line besides the actual point of tangency, is any point on the line above or below the curve? This line, like here to here, is below the curve. So we have an underestimate. Here is our curve. Our tangent line is always, except at the point of tangency, below the curve. So again, an estimate using the tangent line would be an underestimate because the line is literally underneath the curve. Down here, for concave down, F is increasing and decreasing on both of those. Your line for tangency is above the curve, so that is an overestimate. And over here, again, overestimate. Okay, now this is something that you can definitely memorize if that's your deal, or you could just draw out a curve. So we are told that our graph is concave up. How do we know that our graph is concave up? Graphs are concave up when the second derivative is positive. We found our second derivative way back here. So since the second derivative is positive, our graph is concave up. We don't even care if F is increasing or decreasing because the tangent line is always underneath when F is concave up. So here we go. Over versus under because of concavity. That's our third step. Determine whether it's an overestimate or an underestimate based on concavity. Okay, so our graph is concave up. F is concave up because f double prime of x is greater than 0. So f of 1.1, which is about 5.6, is an underestimate because the tangent line is below where that y value really should be. Zoom out so you can see all of that, and we are done.